Okay? So this is another factor that we need to calculate or evaluate in the design and the analysis of our flexural members. Ito yung tinatawag nating CB or yung moment gradient multiplier natin. Okay, so this is from section 506.1 of our NSCP 2015, the moment gradient multiplier, CB. This is sometimes called the lateral torsional buckling modification factor. Okay, so according to our NSCP code, CB is given by this equation. That is equal to 12.5 Mmax over 2.5 Mmax plus 3Ma plus 4Mb plus 3Mc. That should be less than or equal to 3.0. So, pag may moment gradient tayo, gagamitin natin itong equation to solve for the value of our CB. So, don't ask me how did they derive this equation, because actually equations given by the code are results of experiments conducted by the AISC. So, American-based kasi tayo. Yung NSCP code natin is American-based. So, dumaan yan sa mahabang pag-aaral bago nila na-establish yung equation. Okay? So, for us to have a moment gradient, say, yung ating moment, so say we have here a simply supported beam, and this will be our LB. So for us to have a moment gradient, say our bending moment within this unbraced length is not uniform. So pag magkakaroon tayo ng moment na hindi siya uniform, for example that. So yung moment natin is not uniform at any point in our unbraced length. So, iba-iba yung moment natin dito sa points within our unbraced length. Magkakaroon tayo ng CB or yung moment gradient multiplier natin. Okay? So, we have here the definitions of Mmax, Ma, Mb, and Mc doon sa ating CB equation. So, ano nga ba yung Mmax? So, Mmax is the absolute value of maximum moment in the unbraced segment. This is in Newton mm, kilonewton mm, or any unit of moments within our unbraced length, including the endpoints of our unbraced length. So, pag sinabi nating absolute, always positive yan. Kahit sabihin natin yung maximum moment mo sa bending moment diagram mo is negative, i-absolute value mo siya, kaya yung Mmax natin is always positive. Okay? Also, sabi dito that it is within our unbraced length or unbraced segment. So, kukunin mo yung moment within doon sa ating LB. So, for example, dito, kasi yung LB natin, ito. So pag magkakaroon ka ng moment dito, yung Nmax mo, kukunin mo kasi the whole span of LB. Yung LB natin, the whole span. So, kunin mo yung maximum moment dyan. Pag dito naman, for example, yung LB natin, kasi meron tayong supported dito. Supported dito sa gitna, for example. So, yung moment mo, pag, for example, yung andito yung moment mo, ganyan yung moment mo dyan. Yung maximum moment mo is kukunin mo lang within dito sa LB mo. So, pag yan yung maximum moment, yan lang yung maximum moment mo dito sa within our LB. Okay? So, ano naman yung MA? So, yung MA natin is the absolute value. Again, that is always positive of our bending moment at quarter point nung ating unbraced length. Yung ating LB at quarter point. So, for example, dito, kasi ito yung buong span mo is our unbraced length. Yung quarter point niya, pag for example, yung maximum moment dito, yung quarter point ng ating full, so that is LB over 4, andito yung MA natin. Okay? So, pag dito naman, dito lang yung LB natin. So, yung quarter point of our unbraced length, andito siya. So, andito yung MA mo. Okay? So, LB over 4. Yung LB mo is yung kalahati nung buong span mo kasi meron kang support dito sa gitna. So, yan lang yung unbraced length mo. Okay? So, andito yung MA, quarter points. So, pag sinabi naman nating MB, absolute value pa rin siya. So, always positive. This is at the midpoint of our unbraced segment. So, nasa midpoint naman itong MB. So, for example here, ito yung MA natin. So, pag ito yung buong LB natin, ang midpoint andito. So, LB over 2. So, andito yung MB mo. Okay? And dito naman, sa midpoint ng LB, andito yung MB mo. So, yan yung moment dyan. Kukunin mo yung values ng moment dyan. Okay? And for the MC, this is the absolute. Absolute pa rin siya, always positive, at 3/4. So, 3/4, so for example, dyan, that is 3 over 4 of LB. The same dito, 3 over 4 of LB. Andyan yung value mo ng MC. So, kukunin nyo lahat yung values na yan, then substitute it here in our equation CB, masasolve na natin yung moment gradient multiplier natin, which is the CB. Okay? So, ganyan yung pagkuha ng MA, MB, and MC. We also have here an exemption for cantilever or overhang. Where our free end is unbraced, yung CB natin is always equal to 1.0. Pag cantilever or overhang yung ating beam. Okay? And CB is permitted to be conservatively taken as 1.0 for all cases. Pag wala tayong moment gradient multiplier dito. 1.0. So, dito, if our moment within our unbraced length, LB, is uniform. So, pag uniform yung moment natin, pag ito yung moment diagram natin, pare-parehas lang yung moment natin, ito yung moment diagram natin, there is no moment gradient and CB is equal to 1.0. Since yung Mmax, pag kunwari ito yung Mmax, parehas sa MA, parehas sa MB, and parehas sa MC kasi nga uniform yung ating moments. So, yung moment gradient natin is 1.0 pag yung uniform or constant yung moment natin sa ating beam. Okay? Kasi pare-parehas lang yung moment natin dyan. So, sa pagkuha ng moment gradient multiplier, always focus your attention sa pagkuha ng moments within our LB, yung ating unbraced length. So, pag for example, this is our simply supported. Tapos naglagay ka ng support dyan. So, may LB ka dito, may LB ka din dito sa kabila, di ba? So, always get the longer LB. Kukunin mo yung longer at LB since this is more critical doon sa ating bending. So, ito yung kukunin mong LB. And then, solve for the moment, then get your Mmax, Ma, Mb, and Mc to solve for your moment gradient multiplier. Okay? So, let's take a look at an example in getting our moment gradient multiplier. So, we have here sample problem 1. The beam is shown in the figure. So, this is our beam. So, we have concentrated load. It is laterally supported at end. So, simply support siya. The 300 kilonewton, yung 300 kilonewton natin is the service live load. So, service live load itong 300 kilonewton natin. Using factored loads, compute for CB. So, in case A, we have to compute for CB. Do not include the beam weight in the loading. So, wala pa tayong dead load dito due to the beam weight. So, yung i-compute natin na CB due to this service live load alone. Using factor load, so ipa-factor natin yung 300. So, live load yan. So, 1.6 times 300, that is 480. Okay? So, tingin tayo dito. Ito yung drawing natin. So, pinactor natin yung live load natin, that is equal to 480. So, yan lang yung load natin dito sa ating B. So, kukunin natin yung CB pag meron tayong load na point load dito sa gitna. So, formula of CB is equal to 12.5 Mmax over 2.5 Mmax plus 3 Ma, Mb, and Mc. So, kukunin natin yung Mmax, Ma, Mb, and Mc. This should be less than 3.0. So, in your lower design subjects, alam nyo kung paano kumuha ng moment diagram. Diba? So, pinapakita ko lang dito yung pagkuha ko using our shear and then yung moment diagram. Pero pag alam nyo na, kasi, di ba meron tayong formulas, especially pag common load. Pag, di ba, pag uniform load, yung maximum moment niya is equal to 5WL squared over 384 EI and so forth and so on. So, pag may point load, pwede nyo ning makuha yung maximum moment using the formula alone. So, dito, ang ginamit ko is using the shear and moment diagram. This is taken up in your lower design subject. So, I did get my reaction. Nag-drawing ako ng shear diagram and nag-drawing ako ng moment diagram. So, dito sa case A, wala tayong lateral supports in between. Kaya yung LB natin is yung buong span. Ito yung LB natin. Since simply supported is simply support, yung support natin sa left and right will act as the lateral support nung mismong beam natin. Kaya ito yung LB natin. Okay. So, yan yung LB natin, yung full span. So, pag nag-drawing kayo ng moment, ito yung magiging moment diagram ninyo. Okay? So, ang maximum moment dito, andito sa gitna. Ito yung magiging maximum moment natin, which is equal to 720 kilonewton meter. Okay? So, ano yung magiging MA natin? Sabi natin, yung MA is the quarter point of LB. That is, yung LB over 4. So, yung length natin dito is 6 divided by 4. Ilan yun? 1.6 divided by 4. That is 1.5. So, pag length natin is 1.5, ano yung MA natin? Dito sa example natin, linear yung ating moment. Kaya madali nating makuha yung MA natin dito using our similar triangle, di ba? Yung maximum moment natin, 720 at LB over 2, nasa midpoint yung maximum moment natin, that is 3. Diba? So, para makuha natin yung MA, 720 over 3 is equal to MA over 1.5. So, yung value ng MA natin is equal to, so ilan yung value ng MA natin? So, ang MA natin is equal to 360. So, madali nating makuha ito kasi linear lang yung moment diagram natin. Diba? 360. So, MB natin. Ang sabi natin, yung MB natin is within yung bending moment natin in our midpoint. So, yung MB natin is the bending moment at the midpoint of our LB. So, that is LB over 2. So, yung MB natin parehas sa Mmax kasi andito din sa midpoint yung ating Mmax. So, yung MB natin is equal to 370. And for the MC, that is at 3/4 points of LB. So, that is 3/4 over LB. So, 3/4 of 6. So, 3/4 of 6 is equal to 4.5. So, using our linear equations for the similar triangle, that is 720 is to 3, that is MC over, pag 4.5 ito, meron kang 1.5 dito. So, dito yung triangle natin. So, pag ganito ito. So, this is equal also to 360. Yung MC natin is equal to 360. So, meron na tayong MA, MB, MC, and Mmax. We can now substitute these values here in our equation to solve for the CB, which is equal to 1.316. This is less than 3.0. So, yung CB natin is 1.316. Okay? So, yan yung magiging CB natin. And actually, kanina, meron tayong typical values of CB for different types of loading and different points of laterally supported compression flange. Ito yung mga given. So, pag alam nyo ito, you can directly use these values of CB. Pag uniform load, tapos yung lateral support natin is full span, ang CB natin is 1.14. So, kahit di na kayo mag-solve. Ito, yung sa example natin, pinapakita ko lang kung paano na-solve yung CB natin. So, for this example, di ba yung example natin is point load at mid-span, tapos full span yung LB natin, 1.316. So, parehas lang dito. Di ba? Ito yung example natin for letter A. So, that is CB is equal to 1.32. Ito yung example natin sa letter A. We have point load at the mid-span for the full span LB. So, parehas lang sila ng CB. Okay? So, that's for letter A. For letter B, the same problem, this time we have to compute for CB if additional lateral support is provided at mid-span. So, meron tayong additional support provided at mid-span. So, magkakaroon tayo ng lateral support dyan sa mid-span. Do not include the beam weight in the loading. So, hindi pa rin natin isasali yung beam weight ng loading natin. So, wala pa rin tayong dead load. Okay? So, yung live load 300, factored natin yan kasi sabi niya, using factor load. So, 1.6 of 300, that is equal to 480 kilonewton. Okay? So, the same process, shear diagram and moment diagram. Nakuha natin yung moment diagram natin kanina kasi walang pinagkaiba. Yung pinagkaiba lang dito is naglagay tayo ng lateral support at mid-span. So, mayroon tayong support dito sa mid-span. So, yung magiging LB natin dito is equal to meter. So, kanina, yung LB natin is yung full span. Dito, yung LB natin is equal to 3 meter kasi meron tayong support dito sa midspan. Okay? So, the same shear and moment diagram, nakuha natin yung moment diagram. This time, yung MA, MB, MC, and MMAX, ifo-focus lang natin dito sa kalahati kasi andito yung LB natin. Okay? So, pag hindi parehas yan, pag andito yung LB natin, mas malaki dito, dito kayo mag-focus sa mas malaking LB kaysa dun sa mas maliit na distance ng LB. Okay, so dito kasi midspan. So, mag-focus tayo dito sa midspan. Okay? Mmax is the maximum moment that is equal to 720. Yung MA natin is quarter points at quarter points. So, LB over 4, that is 3 over 4. Yung value ng MA natin sa 3 over 4 is equal to 180. Okay? 180. And then, yung MB natin is at LB over 2. So, at 1.5. So, at 1.5, ang MB natin is 360. So, madali lang kunin ito kasi linear. Just have to use the similar triangle. Ito yung triangle natin. Linear naman siya. 720 is to 3 is to MB is to 1.5. Mmax is to 3. MC is to 3 LB over 4. This is 2. I think this is 2.25. Okay? So, makukuha natin yung MC natin is equal to 540. So, 3/4 of 3 is equal to 2.25. Okay. So, meron na tayong MA, MB, and MC. And yung Mmax, substitute lang natin dito sa equation para makuha itong values. So, yung CB natin is equal to 1.67. This is less than 3.0. So, yung answer natin is 1.67. So, pag titignan mo dito, yung, so, ito, CB is equal to 1.67. Parehas. Ito yung letter B natin, di ba? Parehas. That is, yung midpoint natin is nasa midpoint. Tapos, meron tayong lateral support sa midspan. Kaya yung LB natin is equal to L over 2. Kaya yung CB natin is 1.67. That is the same doon sa ating example letter B. Okay? So, for example, for part C, this is C, hindi A. So, for part C, the same example, the same problem. This time, compute pa rin natin yung CB. This time, meron tayong additional lateral support provided at midspan and we have to include the beam weight. So, yung LB natin is 3 meter. Kasi pag maglalagay daw tayo ng support dito sa midspan, meron tayong support dyan, ito na yung magiging LB natin, which is equal to 3 meters. So, magpo-focus tayo dito. Okay? Yung kaibahan lang dito sa B at saka C, dito sa B, include natin yung beam weight nung loading. So, meron na tayong uniform load due to the beam weight. So, ang given is W21/62. So, this is the depth, this is the weight. So, yung weight natin is 62 pounds per feet. That is 92 kilogram per meter. Pag kinonvert natin yan, that is equal to 0.903 kilonewton per meter. So, meron tayong dead load. Dead load yan since that is a beam weight. Weight ng beam na 0.903 kilonewton per meter. Tapos, sabi, using factored load. So, ifa-factor natin yan. Yung live load na 300, that is 480. Tapos, yung WU natin, this is dead load. So, 1.2 times 903. Ito yung magiging value natin. Okay? So, based on your lower design subject, nakuha ninyo ito sa strength of materials, yung paano kumuha ng shear and moment diagram. So, I will not discuss ito in toto na i-discuss kung paano nakuha yung shear and moment diagram. Okay, so this will be your shear and this will be your moment. So, pag pinansin nyo dito sa moment natin, ang moment natin is not linear. Di ba? Parabolic ito. So, pag kinuha nyo gumamit kayo ng geometric, mahihirapan talaga kayong kumuha ng Mmax, MC, MB, values ng MA, MB, MC, and M. Di bale itong Mmax kasi makukuha ninyo pag kumuha kayo ng shear diagram. Ito, yung value ng MC, MB, and MA. Kasi ito, hindi kasi siya linear. Hindi nyo pwedeng gawin yung ginagawa natin na similar triangle pag linear yung moment natin. This is a parabolic. So, para mas madali, kasi pag etong tinitingnan nyo, tas nag-geometric kayo dito sa pagkuha ng MA, MB, MC, mahihirapan kayo. Ang dami-dami nyo pang gagawin. So, pag ganitong parabolic, balik kayo dito sa loading natin. Diba? Na-discuss ninyo yan sa lower design ninyo. Balik kayo dito sa loading natin. So, dito tayo magfo-focus sa loading. Paano makuha ng MB, MC, MB. Kasi alam natin yung mga distances ng MA, that is LB over 4, that is 0.75. Distance ng MB, that is LB over 2, that is 1.5. MC distance is 225. And yung Mmax, yung distance niya is yung sa may 3. Okay? So, alam natin yung distance. So, balik tayo dito sa loading. So, dito sa loading, ito, tingin kayo dito. So, pag nag-cut tayo dyan, pag kinat natin yan, nag-cut tayo, any parts, dito, within our LB. Pag kinat natin yan, pag nag-moment tayo dito, makukuha natin yung moment of MA, MB, MC, and MD. Okay? With the given X. Kasi alam natin na ang MA is within X equal to 0.75. Okay? So, if our X is equal to 0.75, makukuha natin yung MA pag nag-cutting plane tayo sa MA. Just have to take the moment here para makuha ninyo. So, ito. This is for MA at X is equal to 0.75. So, mag-take lang kayo ng moment at 1.75 gamit itong loading natin. So, 3.258 times 0.75 minus. So, minus, that is against the direction nitong reaction natin. 1.0836 times 0.5 times 0.5 over 2. Kasi nag-moment tayo dito. Ang sagot natin is 182.14. So, ito yun na yung magiging MA natin. Okay, so for MB, the same. Pag nag-cutting plane tayo dito at X is equal to 1.5, ano yung magiging MB natin? So, magmo-moment kayo dito. If our X is 1.5, makukuha natin yung MB. So, mag-moment ulit kayo dito. So, MB is equal to 243.258 times 1.5 minus 1.0836 times 1.5 times 1.5.2. Kasi ito is naka-uniform tayo. Okay? That is equal to 363.67 kilonewton meter. That will be our MB. So, for our MC, ito na yung parehas pa rin yung gagawin natin. This time, at X is equal to 2.25. Parehas pa rin yung pagkuha ng MC natin. That is equal to 544.59. And yung maximum natin at midspan, na ang maximum natin as nasa midspan. Ito. So, pwede nyo kunin gamit itong shear diagram natin. Ito. Or pwede din kayo mag-cut at midspan at 3 meter. Tapos, kunin nyo yung moment dyan. Ang lalabas is 724.89. So, meron tayong MA, MB, MC, and Mmax. So, masosolve na natin yung ating moment gradient multiplier, which is equal to CB. Pag sinubstitute natin lahat yan dito sa ating equation, ang value natin is 1.66. That is less than 3.0. So, yung magiging sagot natin is CB is equal to 1.66. So, ganyan ang pagkuha ng CB if not given in the problem. Okay? So, pag ito kasi, mga general loadings lang, may value tayo ng CB. So, pag yung beam mo is iba-iba yung load mo, kailangan mong i-solve yung CV. Pag may moment ka dyan, tapos meron kang load, tapos meron kang moment, kukunin mo yung MA, MB, MC, and M max. Okay? So, eto. Pag may moment ka dito, pwede din itong gamitin. Pag may moment ka, tapos walang load, may moment lang, the same direction at left and right, and M2 is equal to M1, ang CB ninyo is 2.27. Okay? So, dito naman, pag isang moment lang sa left, right, that is M, ang CB mo is equal to 1.67. So, pag magkakaroon ka ng load dyan, mag-iiba na yung CB mo. Okay? The same dito, pag nagdagdag ka ng load dyan, mag-iiba din yung CB mo dito. So, you need to solve for the CB pag wala sa typical values of CB natin. Actually, meron pang ibang drawings, pero ito lang yung kinuha kong typical values for CB. So, para alam nyo lang yung konsepto kung paano mag-solve ng CB pag hindi nyo na-memorize yung mga CB, values ng CB dito sa typical values. Okay? Okay, so this is another factor in the analysis of flexural members, yung ating lateral support condition. Okay? So last time, we have discussed how to check the compactness of our section. So, yung compact, non-compact, and then yung slender elements. So, sa pag-check ng ating compactness, magkakaroon tayo ng idea sa limits ng ating section. So, pagka-compact, yung section limit state natin is yielding at LTB, yung lateral torsional buckling. And yung yan yung possible failure ng ating section. So, pagka non-compact naman, yung limit state natin is yung localized. Pwede sa flange or pwede sa web magkakaroon ng local buckling. Okay, so for the compactness, we can identify the limit state of our section. However, that would not be enough para sabihin na yung limit state ng section natin is yielding or yung lateral torsional buckling. So, kaya meron tayong isang factor which is the lateral support condition of our section. We have to evaluate this in addition doon sa ating compactness ng ating section to truly identify kung anong limit state meron yung ating section. So, in actual, lateral supports are in the form of intermediate beams. Okay? So, for example, I have here a girder. So, meron akong girder dyan. Tapos, meron din akong girder dito. Okay. Meron akong girder dito, tapos meron din akong girder dito. So, dalawa yung... So, let's say, ganyan. Meron akong dalawang girder. Tapos, dito maglalagay ako ng intermediate beam. So, maglalagay ako ng intermediate beam dito. So, maglalagay ako ng intermediate beam. This is to reinforce yung dalawang girder beam ko, yung girder beam ko. So, sa ibabaw ko, ilalagay yung support ko, yung intermediate beam ko. Bakit? Kasi nga, sabi natin, ang lateral support shall be provided to prevent yung LTB or yung tinatawag nating lateral torsional buckling. Okay? So, yung lateral torsional buckling kasi natin acts in our compression zone sa ating section. So, eto, para lang sa, for example, dun sa column natin which is compression, kaya nagkakaroon tayo ng buckling, and for beam, yung load natin just is transverse. Kaya kung nasaan yung compression zone, doon magkakaroon ng lateral torsional buckling. So, For example, di ba pag simply supported yung beam natin, so pag simply supported yung beam natin, that is this, kasi meron tayong support, tapos meron tayong intermediate support dito. Pag maalala nyo pa, in your strength of materials, di ba pag pag simply supported beam, di ba ganyan yan? Pag naglagay tayo ng load, ganyan yung deflection niya. So, yung itong deflection niya, so for example, so yan yung magiging deflection niya. Ito yung neutral axis natin. Ang compression zone natin andito sa taas. At ang tension zone natin andito sa baba. Okay? This is for simply supported. Kaya yung, pag ito yung section natin, so pag ito yung beam natin, ito yung section natin, andito yung neutral axis natin, ang compression zone natin, ito yung compression zone natin sa taas. Kaya, yung paglagay natin ng intermediate beam sa lateral support natin sa ibabaw nung dalawang beam. Okay? So, we will provide lateral support dito sa ibabaw kasi dyan nagkakaroon ng compression zone. Dito, ito yung section natin, dito nagkakaroon ng compression zone, hindi dito sa ilalim. Kasi dito sa ilalim natin is tension. Tension zone na dito sa ilalim. Okay? So, pag naglagay kayo ng support dito sa ilalim, pag naglagay tayo ng lateral support dito sa ilalim, it is not efficient. Kasi nga, yung tension is not critical in lateral torsional buckling. Hindi nagkakaroon ng lateral buckling sa ating tension zone. Kasi di ba't ang ating lateral LTB, nangyayari lang siya sa ating compression zone. So, pag sa ilalim ka naglagay ng lateral support, that would not become efficient. So, parang wala lang. Naglagay ka lang dyan, pero wala namang purpose. Parang ganun yun. Okay? So, kaya sa ibabaw natin nilalagay yung support. If this is a simply supported beam yan. Di ba? Pag kumukuha kayo ng moment, di ba? Pag kumukuha kayo ng moment, pag ganyan, ito yung compression, ito yung tension. Paano pag yung deflection ng moment ninyo? Ganyan naman. Deflection ito deflection, hindi yung moment. Deflection ninyo, ganyan. Ano yung magiging tension ninyo? Ano yung compression ninyo? So, pag ganyan, di ba, na-discuss ninyo yan dati. So, pag ito yung ano natin, pag ganun naman yung deflection nyo, nasaan yung compression, nasaan yung tension zone. Di ba? So, yung naka-smile, that is tension, nakasimangot na deflection, that is compression. So, ganyan. So, pagka-cantilever beam naman, saan maglalagay ng lateral support? If you want to praise the cantilever beam. So, pag cantilever beam, ganyan, di ba, yung cantilever beam. Saan kayo maglalagay ng lateral support? For example, andito yung section natin. Ganyan yung section natin. Sa ilalim. Bakit sa ilalim? Pag cantilever beam. Kasi pag cantilever beam, ang compression zone natin dyan is andito sa ilalim. Ito yung compression zone natin. Pag yung beam natin is a cantilever beam. Doon nagbabakal sa ilalim. Kasi di ba pag naglagay ka ng load dyan, ganyan yan. Ganyan yung magiging deflection niya. And pag nagganyan yung ating section, ito yung neutral axis natin. Ito yung compression zone natin. Ito yung tension zone natin. Kaya naglalagay tayo, pag cantilever beam, nilalagyan natin sa ilalim ng lateral support. Kasi doon nagbabakal sa ilalim. Okay? Andoon yung compression zone pag cantilever beam sa ilalim. So, dyan maglalagay ng support. sa ilalim ng ating cantilever. Okay? So, yan yung concept ng paglalagay ng lateral support. Okay? So, we have here the LB. So, LB is the unbraced length of the beam. The length between points that are either braced against lateral displacement or compression flange on braced against twist of the cross section. This is in mm. So, for example, meron tayo dito. Sa simply supported. Ganyan lang siya. So, yung LB natin is yung buong span niya. So, may simple support dito may support tayo dito sa kaliwa, may support dito tayo dito sa kanan. That will serve as the lateral support pa rin. Ito on its own, kaya yung LB natin is yung full span. So, pag simply supported, ang LB natin is yung full span. Pagka naman meron tayong simply supported, tas naglagay tayo ng lateral support, for example, dito sa gitna, diba? Yung LB natin is, ito na yung magiging LB natin. So, for example, dito, pag naglagay tayo ng support dito, ito yung LB natin. This is also actually yung LB. So, dalawa yung LB natin. Kasi LB ang tawag dito, LB dito, pag naglagay tayo ng support yan. Diba? So, kaya lang, if you compare this to LB, choose whichever is longer since yung mas critical na LB, yung mas mahaba. And yung lateral support natin is nasa compression zone pa rin nung ating beam section. Okay? So, yan yung pag-identify natin kung ano yung value ng LB natin. So, pag alam na natin yung LB, that is the unbraced length. So, nakuha na natin yung LB. Alam na natin yung pagkuha ng LB. Diba? So, yung unbraced length nung ating beam. Meron din tayo ditong tatlong classification na lalabas sa beam natin based on the lateral support condition. Una, yung ating laterally or fully supported beam. Meron din tayong partially supported beam. And yung pangatlo is yung unsupported beam. So, pagka sinabi nating laterally supported, this is also called fully supported. So, eto, ibig sabihin is walang lateral torsional buckling na nangyayari sa ating beam. So, yung ating limit is yielding. Sa pangalawa naman, yung partially medyo lang siya, kaya meron tayong inelastic lateral torsional buckling. And for the unsupported, so pagka unsupported, definitely na meron tayong lateral torsional buckling na mangyayari sa ating beam section. Okay? So, dito sa tatlong classification ng beam, yung laterally, partially, and unsupported, due to support condition, nag-iiba-iba yung MN natin, yung nominal moment natin, yung ating values. So, iba-iba yung values ng nominal moment dito sa tatlong classification ng due to support condition. So, iba yung MN pag laterally supported, iba din yung pagkuha ng MN pag partially, iba din yung pagkuha ng MN sa unsupported. So, tignan natin itong graph dito sa baba. So, yung x-axis natin dito is yung MN. That is MN. And yung this is for the y-axis, and for the x-axis, meron tayong L sub B. So pag titignan natin itong graph, it will actually give you the value of Mn based on the LB or the unbraced length. So, ang first step para magamit itong graph is, una, you have to establish yung ating limits. So, pag maalala nyo, due to the compactness of the section, meron din tayong limits doon. Okay? So, meron tayong limits dito which is the LP and which is the LR. So, andito yung LR natin, andito yung LP natin. Katulad din ito sa may compactness, pag naalala nyo, may limits din tayo dyan, yung lambda R and lambda P. Wherein nakla-classify natin yung beam in terms of compactness doon sa compactness. This time, we classify our beam in terms of our lateral condition. So, isosolve muna natin yung LP, isosolve din natin yung LR. Okay? Then, compare natin dito sa ating L sub P, yung unbraced length natin. So, yung equation natin for MP, LP, L sub P, we have here our equation for L sub P. So, 1.76 Ry, the square root of E over Fy. So, alam naman natin lahat ng variables na yan, di ba? You just have to substitute it in our equation, tapos makukuha na natin yung value ng L sub P. So, the Ry is the radius of gyration about y-axis. Bakit nga ba sa y-axis gagamitin natin dito? Bakit hindi sa Rx? Kasi, hindi ba't nagkakaroon tayo ng lateral torsional buckling? Ang pagbabakol niya is laterally, wherein yung direction ng buckling niya is about the y-axis. Kaya Ry yung ginagamit natin dito. And yung E and Fy is section properties. At ang lalabas na unit natin dito is in, pag naka SI tayo, pag mm dyan, mm yung lalabas kasi magka-cancel yung dalawang unit natin dito. Okay? So, kunwari, for example, tayo ulit dito. So, for example, ito yung limit natin, LP, LR. So, for example lang. So, pag nag-solve tayo, ginamit natin yung equation, ang lumabas na LP natin is equal to 3,000 mm, that is equal to 3 meter. So, for example lang. Tapos, sinolve din natin using the equation of L sub R, yung lumabas na value natin dito is 7,000. That is equal to 7 meter. So, kunwari, yan yung lumabas na values natin pag ginamit natin yung equation sa pag-solve ng LP and L sub R. Say, for example, yung LB ko. So, for case 1, pag yung LB ko is equal to 2 meter, paano natin makla-classify yung ating section based on the lateral support condition? So, pag titignan natin dito sa graph, yung LP ko is 3 meter, yung LR ko is 7 meter. So, yung LB ko, for example, andito siya. That is 2 meter. So, ito yung 2 meter. So, andito yung MN ko. So, ibig sabihin yan, from LB to LP, fully plastic tayo, ibig sabihin, yielding ang mangyayari dito sa ating section. So, that means it falls on the case 1, yung laterally supported, and that is LB is less than or equal to LP, which means it will experience our first limit state, which is yung yielding. And ano naman yung MN natin? So, pag tinitingnan nito, this is horizontal. So, yung MN natin is equal to the MP. Okay? So, mapapansin nyo kasi horizontal yan. Yung MN natin, this is MP. Okay? So, full plastic yan. So, we have full plastics. So, based on the lateral support condition, ma-identify natin yung value natin ng MN niya. Okay? So, if LB ranges from 0 to LP, that is laterally supported. Okay? So, later on, i-discuss natin kung paano or ano yung mga equation to solve for Mn in different condition. So, what if yung LB naman natin is, say, for the second case, what if our LB is equal to 4 meter? Okay. So, this is case A, laterally supported. So, what if our LB is equal to 4 meter? So, pag tinitignan natin yung graph, ang 4 meter, andito. Diba? This is in between 3 meter and 7 meter. So, pag andito yung LB natin, 4 meter, that is greater than LP but less than L sub R. So, ang magiging beam natin is partially supported. So, inelastic lateral torsional backing link yung mangyayari sa ating beam section. Okay? And what if our LB is equal to 8 meter? This is greater than LR. So, andito yung ating L sub B. So, meron din tayong value ng Mn dyan. Meron tayong value ng Mn dyan. Okay? So, if our LB is greater than LR, yung ating beam is an unsupported beam, and yung at meron tayong elastic lateral torsional buckling na mangyayari doon sa ating section. So, pag titignan nyo, iba-iba yung pagkuha ng Mn. Since this is horizontal, this is linear, and this is parabolic. So, magkakaiba yung pagkuha natin ng values ng nominal moment in each case of our support condition. So, kaya iba-iba yung values ng Mn natin. Later. Okay, so again, madali nating mas-solve yung LP. So, tingnan natin yung equation natin. Ito. Kasi yung LP natin is equal to 1.76 RY the square root of EFY. So, madali lang natin isosolve yung value ng L sub P. And sa L sub R naman, yung limit natin, we have this equation. Okay. Ang haba. So, huwag kayong matakot o huwag kayong mabahala dyan sa haba ng equation natin since open formula naman tayo. And again, don't ask me how did they derive with this equation. These are empirical equation based from the laboratory tests done by the experts. So, dito we just have to identify the variables in this in our given equation. So, isa-isahin natin yung variable natin dito sa L sub R. So, meron tayo ditong RTS. Okay. So, ano yung RTS natin? RTS is actually also a radius in gyration. So, saan ulit nangyayari yung lateral torsional buckling? On which part of our section? Diba sa compression zone lang nangyayari ang lateral torsional buckling? So, yung RTS is a special radius of gyration, and that may be approximated accurately and conservatively as the radius of compression flange plus the 1/6 of compression web. So, ito yung RTS natin. So, yung RTS is the radius of gyration lang nung ating compression zone about y-axis. Kasi yun yung buckling natin about y. So, how do we solve for the RTS? We can solve RTS using this equation. So, ito yung equation natin for solving RTS. So, in terms of IY and ang CW, di natin alam yung CW. This is the warp coefficient. So, meron kasing possibility of warping. And CW is given by this formula. So, pagka sinubstitute mo itong CW dito, pag nilagay mo yung equation ng CW dito sa CW, dito sa equation ng RTS, makukuha natin itong simplified equation which is equal to this. So, ito, pag sinubstitute na ito dito, ang kalalabasan, itong equation. Okay? So, that is IY. So, alam natin yung IY. That is the moment of inertia about Y. Tapos, yung SX, that is the section modulus about X. So, yung HO, ito yung hindi pa natin alam. Yung HO. Okay? Or you can approximate yung RTS, yung formula ng RTS, gamit itong equation. Okay? So, itong equation, approximate lang ito. So, itong equation, itong unang equation natin, this is the exact formula nung pagkuha nung RTS. And ito naman, yung pangalawa naman, yung itong RTS, this is the approximate equation. This is given by the code. So, dito sa dalawa, dito tayo sa exact formula. Okay? Ito yung gagamitin natin to solve for the RTS. Unless specified sa given problems in your activity or in your quiz na gagamit kayo ng approximate RTS, value of RTS, ito yung gamitin ninyo. Pero pag walang sinabi, exact formula yung gagamitin natin. Itong equation ng RTS yung gagamitin natin. Okay? So that is for the RTS. That is the radius of compression flange plus 1/6 of the compression web. Kasi nangyayari lang yung ating LTB doon sa ating compression zone doon sa ating section. Okay? So, meron tayong E. Okay, alam natin yan. Properties yan ng steel. FY, properties ng steel. Unahin natin ito. SX, this is also properties, section modulus. Ito, J, this is the torsional constant. And itong C, ito ding HO. So properties, yung FY, properties yung SX, properties is itong E. So, yung J, C, and HO, yung hahanapin natin. So, what is J? J is the torsional constant. Kasi LTV tayo, kaya meron tayong torsion. So, kailangan natin ng torsional constant. Ito yung J, yung torsional constant. And yung C, ano naman itong C? Yung C is actually factor. Ito lang siya. So, for C, for doubly symmetric I-shape, yung C natin is equal to 1.0. And for channel or for singly symmetric like the channel, we have this equation to solve for the value of C. Okay? So, yan yung value ng C natin. So, either for doubly C is equal to 1 or use this equation to solve for C for singly symmetric like the channel. And for the HO, ano naman yung ating HO? Okay? So, for HO, we have HO is the distance between flange centroid in mm or in inches. So, basically, D minus TF. So, pag tinitingnan natin, ito yung HO. So, andito yung gitna ng flange, andito yung gitna ng flange natin. So, pag kinuha natin yan, yan yung magiging HO natin. So, this is D. This is, yung sa taas, this is 1/2 of TF. Sa baba naman, 1/2 of TF. Kasi andito yung gitna natin, di ba? Nasa 1/2 of TF yung gitna. So, ito yung HO natin. Kaya D minus TF kasi half dito sa baba, half dito sa taas, kaya mag-iisang TF na yan. So, yung HO natin is the distance between flange centroid that is equal to D minus TF. This is for the I wide flange S section. Parehas lang dito sa channel. Ito din yung HO, yung between flange centroids pa rin siya. So, D minus TF pa rin siya, yung thickness ng flange. Kasi 1/2 dito, 1/2 din. So, kaya mag-iisang thickness ng flange na siya. So, that is for HO. And for the J, that is for the torsional constant. This is actually a property of section, which has something to do with the resistance against torsion, itong torsional constant natin. So basically, the higher value of J, yung torsion, the higher the resistance. Torsional constant, the higher the resistance against nung torsion natin. So, pag maalala nyo, di ba, if generally speaking, pag meron tayong rectangular, ito yung P natin, ito yung T natin. Ang J natin is equal to BT cube over 3. If you still remember yung lower design subject ninyo, actually, this is all from strength of materials. So, yan yung general formula natin pagka rectangular yung section natin. Kaya lang yung I shape and C section natin is hindi lang basta rectangular. So, bale ang ginagawa natin, dinidivide natin yung ating section into rectangular. Okay? So, kaya meron tayo dito sa channel, meron tayong given dito. Diba? So, pagka dinivide natin ito isang rectangular ito. Okay? Ito, isang rectangular ito. Tapos ito, isang rectangular din. Ito. Okay? So, kaya BO. So, ito yung BO. So, ito yung B. T. Yung T cube. TF. Kasi ito yung thickness natin. TF. So, TF cube. So, times 2. Kasi dalawang flange ito sa taas and sa baba. Kaya times 2. Plus, ito naman. Yung sa ating, sa web. So, yung HO natin times yung sa thickness and then cube. Kasi yung BO natin is hanggang dito. BO natin. Hanggang dito. Okay? So, yung J natin for the web, ito. So, H over T cube over 3. And the same dito sa I shape. Ginagawa rin lang nating rectangular ito, tapos isang rectangular para makuha natin itong equation for the torsional constant J. Okay? So, in the properties of steel section, maalala nyo, meron tayong isang J doon, di ba? Yung polar moment of inertia. So, iba ito Iba yung J na polar moment of inertia dito sa torsional constant na J. So, this is different J. Yung polar moment of inertia kasi J din yung ating variable doon. So, iba yon. Iba yung torsional constant dito. Okay? So, that is for the J. So, pag alam na nating lahat yung ating variables, yung values ng variables natin using these equations, substitute lang natin dito para ma-solve natin yung limit na L sub R. Okay? So, ganyan yung pag-solve natin ng L sub P, L sub R, and L sub B. This is to determine the support conditions nung ating section. If it's laterally or fully supported, pag partially or unsupported. Okay? So, pagka nakuha ninyo yung lateral support condition, yung compactness, yung CB natin, okay? We're now ready to compute for the nominal moment strength of our flexural member. So, importante ito sa pag-design and pag-analysis ng ating flexural members. Okay, so we have here the procedure for computation of the nominal moment strength. However, this procedure is only limited to I and C-shaped section bent about the major axis. Okay, so this is the most used or common type of structural members, yung I and C shape. So major axis tayo, kaya meron tayong X dyan, MNX. Okay, so MNX. For other section, tingnan nyo na lang sa NSCP ninyo. Okay? Meron yung mga equations for other sections. So, we will just focus on I and C shape section since this is the most common structural member used in steel, construction of steel building. Okay? Okay, so for the bending, medyo marami tayong i-check dito. Okay? So, meron tayong procedures dito. First procedure natin is in solving MNX is to check our compactness. So, how do we do that? So, in our previous lesson, kailangan nating i-classify yung section natin whether compact, non-compact, or slender. By comparing yung lambda natin with our limits lambda r and lambda p. Diba? This is given by the code. So, I hope you still remember that previous topic of ours. Okay? So, in checking the compactness of elements, we will now determine the compactness of our section. Okay, so from this step, we will be getting an answer which is either compact or non-compact or slender. Diba? Tatlo yan. So, dito sa step 1 natin, either compact, non-compact, or slender ang kukunin natin. So, pag slender yung nakuha natin, remember, we don't want to have a section that is slender. So, pag kaganyan yung section natin, we have to improve or we have to replace our section such that yung ating compactness would not result to a slender section. Kasi ayaw natin ng slender. So, kailangan nating improve yung ating section pag nagkaroon tayo ng slender element. Okay? So, sa first step, sa first procedure natin, ang sagot lang dapat natin is compact or non-compact. Okay? So, pag ang nakuha ninyo is slender, revise the section. You have to improve the section para hindi maging slender. Kasi nga, ayaw natin ng slender element. Okay? So, in your step 1, either compact or non-compact yung makukuha ninyong compactness nung section. Okay? So, in reality yun. In reality, yung slender, kailangan nating palitan kasi ayaw nating magkaroon ng slender element. Okay? So, and from there, yung from our step 1, what could be our next step? So, if our answer here in our step 1 is compact, we have to proceed to our second step. This is the for compact section. So, for compact section, we have to check for the lateral torsional buckling, yung LTB natin, by checking our lateral support condition. So, we have to check L sub B versus L sub P and L sub R. Kasi if we have compact section, meron tayong ma-experience na limit state which is either yielding or LTB. So, either of these two, pag compact section yung nakuha nating compactness. Okay? So, paano mo ngayon malalaman kung magkakaroon tayo ng LTB, yung lateral torsional buckling? This is to check dito sa ating lateral support condition. Diba? So, so support condition natin, we have fully supported, meron tayong partially supported, and meron naman tayong laterally unsupported. And malalaman natin kung anong condition ng support natin by comparing yung LB with our LPN and LR. Okay? So, pag kinumpare natin dyan, pag yung lumabas, meron tayong given equation to solve for the LPN, LR. Okay? So, if we have fully supported, if our LB is less than or equal to L sub P, we have a laterally supported. So if we have this fully supported or laterally supported section, LTB will not happen. So wala tayong LTB dito pag laterally supported. Okay? So ano na ngayon yung magiging failure natin kung wala tayong LTB? If our LTB will not occur for laterally supported section, that would be yielding. So, yielding tayo pag laterally supported. Okay? So, pagka naman partially supported, what will happen? Meron tayong inelastic LTB. And yung MN natin is linear, tas pagka unsupported naman, magkakaroon tayo ng elastic LTB. And yung MN natin is a non-linear. Actually, this is yung sa parabola doon sa graph natin, yung second degree na siya. Okay? Pag maalala yun yung graph natin sa previous slide natin. Okay? So, with this step number 2, so for compact section, you will determine the condition of your support that would lead us to the formula to be used in computing or in solving the value of Mn. Yun yung hinahanap natin, yung nominal moment. Okay? So again, if we have LB is less than LP, laterally supported, wala tayong LTP, yung Mn natin is equal to MP kasi fully plastic tayo. That is equal to Fy times D. Okay? So pagka yielding naman, so pagka yielding, kasi yielding ito kaya MP is equal to Fy Z. Walang LTB, kaya plastic moment, kaya Fy times Z. Yielding yung magiging failure natin dito pag laterally supported. If LP is less than LB and if LB is greater than LP but less than LR, meron tayong partially supported and there is an inelastic LTP. So yung Mn natin, gagamitin nating equation to solve for Mn is this equation. So ito yung magiging equation natin for Mn. So we have CB, yung gradient multiplier natin. Alam natin kung paano mag-solve ng CB. Yung MP natin, okay? Still, this would be equal to our plastic moment, that is Fy Zx. Okay? And yung iba, ito, mga properties ng steel. And syempre, yung LB, LP, and LR, solve nyo muna yan, di ba? So, meron na kayong values niyan. Okay? So, dito sa equation natin, we have to multiply. So, meron tayong isang kindly check this. Meron tayong bracket dito. Ayan, meron tayong bracket dyan. So, in our equation, you have to be reminded that we have to multiply this equation first. I-multiply muna natin itong equation. So, dyan karamihan nagkakamali. Nina-minus agad nila ito. So, i-multiply muna natin itong equation and close by this parenthesis bago natin siya i-subtract dito sa MP. Okay? And our value for N should not exceed our MP. Okay, so may limit pa rin tayo dyan. So, paano pag yung value dito is nag-exceed? Paano pag yung mas malaki yung MN ninyo kaysa MP? Bawal yun. So, for that case, ang gagamitin mong MN is equal to the MP. So, pag yung value mo na MN exceeds MP, ito yung gagamitin mo in the design. So, pagka nag-design ka na, kung mas malaki to yung itong MN. Kasi nga may limit tayo, this should not exceed to our MP. Okay? However, ganun yung gagawin natin. However, in our activities, or maybe in our exam or quiz, pag yung one required doon, for example, 3 required, tapos yung isang required doon is you have to give me the calculated MN. So, pag sinabi kong you have to give me the calculated MN, your answer should be the value of MN kahit nag-exceed siya ng MP. Kasi calculated yung tinatanong ko. Kaya yung ibibigay yung sagot sa akin is yung na-calculate yung MN. Okay? Using the equation, kahit na mas greater siya sa MP. Yung actual na na-compute nyo ng MN, yun yung magiging sagot dapat ninyo. Pag yung tanong ko sa aking, for example, nagpa-activity ako, tapos ang tanong ko is give me the calculated MN. Yung mismong na-compute ninyo, yung actual na na-compute nyo na MN, yun yung ibibigay nyo sa akin. Pero pag ang tanong ko naman is, what is the design strength? So, di ba pag LRFT, that is the design strength. Pag AST, ganyan. That is the allowable for the AST. So, pag sinabi kong design strength, yung pag sinabi kong design strength, yung ibibigay nyo sa akin, yung magiging value nyo ng MN dito is, pag mas mataas yung MN dito sa na-compute nyo ninyo dito, yung ilalagay yung MN dito is yung equal to the MP. Pag yung MN ninyo is greater than MP. So, kukunin nyo na yung correct value dito, yun yung sa-substitute nyo dun sa design strength. Okay? So, pag tanong ko is, pag design strength, you have to give me the value of MN which is not greater than our MP. Kasi design na yung tinatanong ko. Ang gagamitin nyo dapat dyan should not exceed the value of our MP. So, pag mas mataas yung MN, ang gagamitin nyo dito is MP. Okay? So, ganyan. And if our LB is greater than LR, that is laterally unsupported, there is an elastic LTB, yung MN natin is equal to this equation. FCR-SX, this is less than or equal to MP pa rin siya. Okay? Where yung FCR, this is the property of scale, yung FCR natin is given by this equation. Okay? So, yung E natin, modulus of elasticity, torsional, yung SX, yung HO. So, alam naman ninyo lahat ng variables na yan. So, alam ninyong isolve. So, pag alam nyo yan, substitute nyo lang dito sa equation to solve for the value of FCR. And then, isa-substitute yung FCR dito, makukuha na nyo yung nominal moment. So, yung nominal moment should not exceed our MP. Okay? So, this second step is for compact section. So, pag sa step 1, compact section, dito kayo titingin. So, pag sa step 1, ang sagot ninyo, if you check the compactness, tapos naging non-compact yung ating section, dito naman kayo tutuloy. Dito. Sa step 3. So, this is for the non-compact. Okay? So, anong mangyayari pagka ang compactness mo is non-compact? Pwede tayong magkaroon ng local buckling, specifically doon sa ating flange element. So, specifically sa flange element. Kasi kadalasan nagiging non-compact ang ating section dahil doon sa ating flange. Kasi kadalasan ito yung element na lumalabas, kadalasan is flange, yung non-compact, kaya nagiging non-compact din yung ating section, yung buong section natin. Kaya for the non-compact, we have two. We have to check for the flange local buckling and we have to check for our LTB. Okay? So for the flange local buckling, if lambda is less than or equal to lambda p, that is compact, no flange buckling ito. Wala tayong local flange buckling. And if lambda is greater than lambda p but less than lambda r, that is non-compact, there is a flange local buckling. So pag ito yung lumabas, pag chinek niyo yung flange local buckling, wala tayong pag ito yung lumabas, compact, hindi niyo na kailangang i-solve itong flange local buckling, punta na lang kayo dito sa lateral torsional buckling. So remember, for non-compact, dalawa yung i-check ninyo, yung FLB and yung LTB. Okay? So ito, i-check nyo ito, tapos i-check nyo ito. So kukunin nyo yung yung mas malaki or yung mas maliit. So you will get the nominal strength that is the smaller value. So kung ano yung mas maliit, yun yung kukunin yung value ng MN between the FLB and LTB. Okay? So sa pag-check ng FLB, pag ang lumabas compact, wala tayong flange local buckling, kahit hindi nyo na i-check ito, punta na lang kayo sa LTB. Okay? So pag non-compact naman, meron tayong flange local buckling. So ito yung gagamitin nating equation to solve for the nominal moment, MN. Okay? So, MP is equal to FYZ pa rin siya. Okay? So, alam yung pagkuha ng mga values ng variables na yan, substitute nyo lang yan, makukuha natin yung value ng MN. Okay, yun yung unang i-check ninyo. Yung pangalawang i-check ninyo is yung LTB. Okay? So, pag laterally supported, partially, and laterally unsupported. So, pag laterally supported yung LTB, ito yung gagamitin nating equation. Pag partially supported, ito yung gagamitin nating equation. And pag laterally unsupported, ito yung gagamitin nating equation. Okay? So, basically dito, meron kayong masosolve na MN dito. Pag non-compact lang yung nakuha nito, may value tayo ng MN dito. Tapos, in LTB, meron din tayong value na makukuha dito. Okay? So, dalawa yung MN na makukuha nyo if you check for FLB and LTB. Pag non-compact lang ito, may value ng MN. Pag compact dito sa FLB, wala tayong MN dito. Ito lang yung meron tayong MN sa LTB. So, pagka dalawa yung nakuha ninyong MN, ano yung gagamitin nating MN? So, yung mas maliit sa kanilang dalawa, sa FLB or sa LTB, yun yung gagamitin natin in our design. Yung value ng MN. So, huwag kalimutan yung value ng MN in our design strength should be less than or equal to MP. So, huwag kakalimutan yan . So, pag yung MN mo is mas malaki sa MP, ang gagamitin mo sa design is yung value ng MP. Kasi bawal nga tayong mag-exceed ng MP. Okay? So, you have to familiarize yourself kung saan gagamitin yung mga equation, yung mga formula na binigay natin. Okay? So, ang pagkahaba-haba ng analysis natin for flexural members. Ang importante dito is alam nyo kung saan nyo gagamitin yung mga variables natin. Kung alam nyo kung anong gagamitin na equation sa compact, non-compact, if yung laterally supported, partially supported, and laterally unsupported. Okay? So, you have to familiarize yourself and you have to familiarize yourself in the given variables and equations and formulas in the analysis and design of the flexural members para hindi kayo mahirapan pagdating ng activity and then sa exam or quiz. Okay? So that is for the procedure for the computation of nominal moment strength. Okay, for the sample problems, I will discuss this next meeting for the sample problems.